So now we're ready to walk through and to do some examples of inferences for population proportions. And the first is really just an example that I wanted to talk about so that we can get a hang of exactly what we're doing, right? I want to figure out exactly how all of this works. And according to some poll, it turns out that 57% of those polled said that they were worried about the privacy of their financial information when they file taxes online. Okay, a good mid-April problem here. The survey, really what the content of the survey is doesn't matter, but the survey had a margin of error of plus or minus 3% for a 95% confidence interval, and I want to know how do we interpret this. So what I mean is, how do we interpret this? So if we have a margin of error of 3%, we can be 95% confident. So we can be 95% confident that our population proportion P, here P is going to be the population proportion for the number of people worried about their financial information for online taxes. Worried about online taxes. We're just using a shortcut here, and we know that our population P, we can be 95% confident that P is in the interval from 0.54 to 0.60, right? Somewhere between 54% and 60%. If we take that 57% plus or minus 3%, right? This is really 57% plus or minus our 3%. Okay, that's really all that tells you. We can be 95% confident that the population proportion is somewhere in that interval, right? Again, the margin of error is the thing after the plus or minus. So that's the relationship here. Okay, that's really all I wanted to say with example 1. For the rest of these examples, I want to actually compute how all this is going to work. Okay, and so what I want to do is I want to go through and I want to actually compute how all this is, where to put everything. And so what we're going to do is we're going to look at the first example here. Oh, man. So what I want to do next is for number 2. For number 2, and for the rest of these, actually, I'm not going to give you all of the outcomes necessarily, all of the statistics. Maybe we'll have to compute them, but I want to kind of start to piece together where everything goes. And so a March 2020 internet poll, I'm sure it was a super reliable poll, probably not, just kidding. But a March 2020 internet poll compared the debate performances of the two Democratic candidates, the two major Democratic candidates, Joe Biden and Bernie Sanders, in their March 2020 debate. The poll was of 24,091 participants. And of those 24,000 plus participants, 78.13% thought that Bernie won the debate. I'm not going to worry. There was a different percentage that thought, so it was, I forget exactly what the number was, but something like 15% that thought that Joe Biden won the debate. And then there was also a certain percentage that either did not have an opinion or were unsure, or whatever that third category is. Okay, but all I'm worried about is the percentage of people that thought that Bernie Sanders won the debate. And what I want to do is I want to find a 95% confidence interval for that population proportion, right? I want to know of the population of all the people, what is the proportion of people that thought Bernie Sanders won the debate? So we're going to use our survey of 24,000 people, and our confidence interval is going to be just nothing more than, remember that our formula for the confidence interval is it's going to be the sample proportion, that's the 0.7813, plus or minus our cutoff, z sub alpha over 2, times the square root of p hat times 1 minus p hat over n. And this is going to be 0.7813. If alpha is 0.05, then z sub alpha over 2 is going to be 1.960. You get that value from, you can get it either from the handout that I've put for the z table and t table for the handout on Canvas. You can get that from R itself, right? If you were to type in R, if you were to type in what is that critical value, right? That's the Q norm. And so just as a reminder, this 1.960 would be Q norm 0.975, because you take that 5%, split it in half, that's 2.5%, and so that would give you 1.960, at least to 3 decimal places. Anyway, so that's your cutoff value, and then times the square root of p hat times 1 minus p hat all over n. And so that's going to end up being 0.7813. Okay, so 0.7813 times 1 minus 0.7813 all over n. N was our sample size. That was the 24,091. And it turns out when you actually crunch these numbers, you get 0.7183 plus or minus 0.0052. Okay, so you end up with 0.7813. I actually want to just use this to 0.52. I meant to write this as an interval. Okay, 0.7813. That's really, you could also write this as a confidence interval, where the confidence interval is 0.7761 to 0.7865. So you can be 95% confident that the population proportion of people that thought that Bernie won the debate is between 77.61% and 78.65%. That's what that tells us. Okay. What I want to do next is basically the same thing. I want to find a confidence interval. Here it's a 99% confidence interval, and we're going to do this for the proportion of Americans who have ever graduated college. We want to figure out what proportion of Americans have graduated college. To do this, we conducted a survey. We got 473 participants that were over the age of 25 that were asked whether or not they ever graduated college. And so we want to get a 99% confidence interval. And so what we have to do here is we have to compute. It's really going to be the same as number 2, except we just need to compute p hat. P hat is going to be the number of members of our survey that have graduated college divided by the sample size of our survey. So 158 divided by 473. And again, if you plug all this in, you get 0.3340. That happens to be the population, the sample proportion. We have a 99% confidence interval. That means the alpha is 0.01. And therefore, z sub alpha over 2 is going to be, so if alpha is 0.01, then z sub alpha over 2 is going to be 2.576. Again, one of the big cutoffs. Again, that's on the, it's actually on the bottom of the t distribution, even though it's a z distribution quantity. It's just that it happened to fit better on that back side of the PDF there. Or you can use R. Again, the same way as above. I'll leave that to you to figure out exactly how to do that. But it turns out that our confidence interval is going to be 0.3340 plus or minus. There's no reason. I'm being slightly inconsistent here with my decimals. Let's just do it to 3 decimal places. So 0.334 plus or minus our critical value, 2.576, times the square root of 0.334 times 1 minus that, so that's 0.666, all over our sample size, which is 473. And so it turns out that our confidence interval is going to be 0.334 plus or minus, we'll have a margin of error of 0.056. Okay, so that tells us that somewhere between, 33.4% plus or minus 5.6% of people over the age of 25 have graduated college. That's what we got from our example. Our last 3 examples, we're going to look at crunching a few more numbers here. They're going to be a little bit more math involved. And what I want to do first is I want to figure out how large of a sample would we need to guarantee a margin of error of at most 1%, assuming that we have first a 90% confidence interval, and then for a 99% confidence interval, we are not going to assume that we know anything at all about what the sample proportion should be. So that means, so if you remember back when we were talking about the guesses for the sample proportion, we're going to use 1/2 for the guess. So in other words, 1/4 is going to go in front of our quantity. So we know that n is going to be 1/4, times z sub alpha over 2, all divided by e squared. And again, this 1/4 comes about because we're not making any assumptions about what the sample proportion should be. So this is the most conservative value that we can have. And if we have a 90% confidence interval, okay, so if we have a 90% confidence interval, the way that this is going to work is that for the 90% confidence interval, our n is going to be 1/4 times our alpha, so z sub alpha over 2 is going to be 1.645, divided by our margin of error, which we want to be 0.01, and that's going to be squared. And it turns out when we actually square all this for n, what we're going to end up with is 6,765.062, which means that the minimum sample size that we need to have a margin of error of at most 1% would be whatever this is. We're just going to round up to the nearest integer. Round is kind of a strange word to use here because we're not rounding to the nearest integer, we're always rounding up. So in our case, it's going to be 6,766. That's going to be our n. Okay, so that's our answer for the 90% confidence interval. And after that, let's do, I want to do the same thing, but for a 99% confidence interval. Our formula is going to be the same. We're going to have n is 1/4. Our z sub alpha over 2 is going to be 2.576. Our margin of error will still be 0.01. When we square this, we're going to end up with 16,000, okay, 589.44. And so if we round up, this is going to be 16,590. That's going to be the minimum sample size. That's quite a sample size, but that's going to be the minimum sample size that we need in order to have a margin of error of at most 1%. Okay, so again, this was for 90%, and 99%. And again, we use the 1/4 because we assume that we do not have an estimate for p hat ahead of time. All right, next is number 5. In a survey of 1,008 American adults, it was found that 534 of them disapproved of the Patriot Act. And what we want to know is at the 5% significance level, do the data provide sufficient evidence to conclude that a majority of American adults disapprove of the legislation? Here, a majority just means more than 50%. And so what we're going to do is we're going to set up our hypothesis testing, where our null hypothesis is going to be that the population that supports this is going to be 0.5. Our alternative hypothesis is going to be that the population is greater than 0.5, right? That's what we want to know, is do a majority of Americans disapprove of it or not? Our n, so we can get a few things here. We know that our n is 1,008. This means that our sample proportion, p hat, is going to be 534 over 1,008. That turns out to be 0.5298. So certainly more than 50% of the sample disapproves of the legislation. What we want to know is, can we infer from that more than 50% of the population disapproves of the legislation, right? That's a more subtle question. But does this carry over to the population is the question. How certain are we of this? So what we're going to do is we're going to compute our test statistic. Okay, so we're going to compute our test statistic Z0. And remember, our test statistic Z0 was, if we remember, it was p hat minus p0 all over the square root of p0 times 1 minus p0 over n. So here p hat is 0.5298. p0 is the value that we're testing, so that's the 0.5 value. So that's the value that we're trying to have as our null hypothesis, is that the population is equal to 0.5, so that's 0.5. And then in the denominator, we're going to put in what we get. We're going to put in, let's see, p0 is 0.5, so this is 0.5 times 1 minus 0.5 all over n. N was 1,008. And it turns out when you crunch the numbers, what you're going to end up with is a z-value of 1.8956. And so if you do this the critical value way, so with the critical value approach, for the critical value, if we want a 5% significance level, notice that this is a right-tailed alternative hypothesis. So all we need to do is to figure out what's the cutoff so that under, in this area here, we want only 5% there. And it turns out that the cutoff is 1.645. Our value is above that cutoff, right? So Z naught is greater than our critical value. So that means that we reject the null hypothesis. Alternatively, you can do the p-value approach, where what you're going to do is you're going to compute the p-value, and it turns out that take the p-value, and your p-value is going to be 0.0290, since that's less than alpha, right? Our alpha was our significance level, which was 5%. This is less than 5%, so that again means reject the null hypothesis. Okay, so that's the p-value approach and the critical value approach. Of course, they'll always agree. It's just whichever one you prefer. Okay, the critical value approach is probably easiest if you don't have a lot of technology, right? If you don't want to have to rely on R to compute everything here, you can use the critical value approach. The p-value approach, though, gives you a little bit more information, if you think about it, than the critical value approach. So the p-value approach actually tells you what would your significance have to be in order to reject the null hypothesis, right? And so this tells you a little bit more. This tells you that not only would you reject the null hypothesis at the 5% significance level, you would also reject it at the 3% significance level. You would not reject it at, say, the 2% significance level. So the p-value does give you a little bit more information, but you just need to have some technology around in order to compute the actual p-value. So number 6 said that there was a sample of 335 people, and 167 of them voted in the 2008 presidential election. It was later found that of 208 people, 94 voted in the 2012 presidential election. And what we want to conclude is, can we be 95% confident that fewer people voted in the later election than in the earlier election? So has there been a decrease in the number of voters? And what we're going to do is we're going to compute everything. We're going to have P1 hat. So this will be the sample of our this will be the proportion of our first sample. That'll be 167 over 335. That turns out to be 0.4985. So 0.4985, just good to 4 decimal places. The second sample proportion is going to be 94 out of 208. That's going to be 0.4519. And then our pooled sample proportion will be 167 plus 94 over 335 plus 208. So remember that means that you group the two samples together, and then you figure out how many people voted divided by the size of the sum of the samples. The sum of the sample sizes. And so this turns out to be 0.4817. Okay. And then what we're going to do is we're going to compute our test statistic. Our test statistic is going to be P1 hat minus P2 hat over the square root of P hat sub P times 1 minus P hat sub P times 1 over N1 plus 1 over N plus 1 over N2. Okay, and so I'm not going to write this all out. I'll let you fill in the details here, but this is going to work out to be 1.0561. Okay, so there's our test statistic. Our critical value is 1.645. Okay, so 1.645. So remember that the picture that you should think of is we have our normal distribution. We have our critical value of 1.645. We're trying to figure out if this is greater or not. So we want to know is our value over here, and our value of 1.0561 is somewhere over here. Right, so that's our test statistic, 1.0561. So that means that we do not reject the null hypothesis. In other words, we cannot be 95% confident that fewer people voted. It's possible there's enough wiggle room here that maybe these are just we're within the margin of error, right? We can't be certain. So next what we're going to do is we're going to find a 95% confidence interval for P1 minus P2, where P1 and P2 are the population proportions. And when you can do one-sided confidence intervals, but we've never talked about it. For us in our class, all confidence intervals are two-sided. And so what we're going to do is we're just going to follow everything in our formula. We know that our confidence interval is going to be P1 hat minus P2 hat plus or minus our cutoff, Z sub alpha over 2, times our square root term, which is going to be P1 hat times 1 minus P1 hat all over N1 plus P2 hat times 1 minus P2 hat all over N2. And it turns out that when we plug in everything, what we're going to get for the difference P1 hat minus P2 hat is going to be this 0.4985 minus 0.4519. So that's going to end up being 0.0466. And then when we plug in everything else, we're going to end up with our margin of error being 0.0863. Okay, so what that tells us is that our population P1 minus P2 is going to be somewhere in the interval from 0.0466 minus 0.0863, so that's negative, I need to make sure I round this correctly, negative 0.0397, all the way up to 0.1328. This is a really wide interval, if we think about it. What this is saying is that the difference between P1 and P2, possibly, by the way, I should point out, the difference between P1 and P2 could be negative. That would mean that P2 could be larger than P1. That's why we couldn't conclude before. I mean, this is slightly different because for Part B, we have a two-sided test. For Part A, we have a one-sided test, but this does agree with the fact that since P1 minus P2 can be negative, that means that we can't really be sure that P2 is less than P1, right? Because if it's greater than P1, then it would be negative. And we're certainly allowing for that to happen just based on the fact that we have a negative endpoint for our confidence interval. And the confidence interval, remember, is not for the proportions themselves, just for the difference of the proportions. So it's okay for it to be negative. But this is a really wide interval, right? We have a margin of error of almost 9%, say 0.63%. That's a really big margin of error. So as useful as these confidence intervals are, confidence intervals for two population proportions are not super useful. Okay, so they just don't get used too much. What I want to do next is I'm going to show you, I found some documentation on R of how to implement this proportion test. So there's a function here called prop.test, and this is going to bring up all the documentation that we need. So I'll go over that. I'll add this to the Google documents that we have. But that prop.test function is exactly the thing that we're looking for. So what I want to do is I want to quickly run through the examples again and show you how to implement this proportion test for the different scenarios. Number one, actually, we don't have any values, so there's nothing to plug in. So let's start with number two. So number two is the one where we had 24,091 participants. 78.13% thought that Bernie Sanders won the debate. We wanted to find a 95% confidence interval. And so what we're going to do is we're going to say prop.test. And what goes first is the number of successes, right? The percentage that thought that he won the debate. So that was 0.7183. So you can calculate this ahead of time if you want, or you can just put, we're going to take 78.13% of the 24,091 participants of the poll, So the first value here that we're going to put in is the number of people that have whatever characteristic we want. That's what we call x, right? So remember, p hat was x over n. This is our x. So it's something like 18,000. If I remember, it's 18,822, I think, is the number that goes there. Anyways, it doesn't matter. So the next thing that we're going to do is the number of people that were polled. So 24,091. And there's a correction term. There's kind of some fancy things that people can do with proportion tests. We do not do the correction. So we're always going to have correct equals false. By default, I should just point out, if you look down here, it's always going to say correct equals true. We want that to be false. Okay, we are not going to add in the correction term there. And that's it. So we can, since it's a confidence interval, like I was just saying, this is going to be a two-sided confidence interval. We don't need to do anything fancy. Other than that, here is what we're going to get, and here's our confidence interval. Right? That's what we found before. So 0.7760. I guess in our case we found 0.7761 because we were just rounding, but that's fine. 0.7760 all the way up to 0.7865. That was the upper bound that we found for our confidence interval, and we're done. Okay, that's really as simple as it gets there. What we're going to do next for number 3 is we had, of 473 Americans, 158 said that they had completed college, find a 99% confidence interval. So we're going to again do the prop test. We put in the number of successes, so that's 158. Then the sample size of the poll, so that's 473. And then we're going to add the confidence level of 0.99, and our correct will be false. We're going to not do the correction term here. And we get a confidence interval. This is exactly the confidence interval that we found before. Pretty cool, not that much work. That's how this is going to be helpful for us. So we're done with number 3. Number 4 was the question of how large of a sample size do we need to guarantee a certain margin of error. And this is one that I'm going to stick with my earlier assertion that there is no good test in R for this. There's certain packages that have this built in. I'm not going to worry about having you install any different packages. If you feel like being super fancy and installing packages, go for it. In this case, I think it's easier just to do the, it's a multiplication and the formula is there. The formula is straightforward. So it's easier just to do that multiplication than it is to worry about installing packages, in my opinion, for us in this context. So I'm going to skip number 4. Number 5, here we're going to actually do a hypothesis test. So we'll talk about exactly how to do this. What we wanted to know is, of 1,008 American adults, it was found that 534 disapproved of the Patriot Act. And so at the 5% significance level, meaning we want a 95% confidence, can we conclude that the majority of Americans disapprove of the legislation? So if you remember, we had the null hypothesis being that our proportion was 0.5. The alternative hypothesis was that the proportion was greater than 0.5. And other than that, we're going to plug everything in to R and let this do its magic. So our proportion test that we're looking at, our proportion test, we have, 534 disapprove. That was out of a sample size of 1,008. The probability that we're trying to test against is 0.5. Our alternative is greater, and we want the correction to be off. And if we do that, we end up with all the stuff that we had, before. So let's see. So if we do this, we're going to end up with our null probability was 0.5. Our p-value, this might be the easiest way to look at this. I thought that this spit out the test statistic, but it does not seem to do that. Our test statistic we found to be 1.8956. So you could find the test statistic if you want by looking at let's see, we would have to look at the Q norm of 0.2939. Something is a little bit fishy here. But the p-value is correct. I'm not sure what's happening with the test statistic. It might just not compute it, but our p-value is correct. We found our p-value to be 0.0290. That's what we found when we did this. So here, if we're not rounding, we get 0.0294. Okay, so since we have a 5% significance level, we'll reject the null hypothesis, and there we go. Okay, so that's how we'll do number 5. Again, I'm not sure exactly where that test statistic went, but we'll have to look at that. We will have to look at that. Actually, one thing I want to try just very quickly, trying something on video is dangerous here, but let's try this. So we have 534, 1008. Our alternative is greater. And there we go. That's the same story here. So this is the one sample proportion test without the continuity correction. We get our p-value is the same. Okay, that's fine. So our final example, number 6, we had, this is going to be the 2 sample proportion. And so if you remember with the prop.test function, if we look down here, our xn, so our x, so this value here, is the number of successes. Our n is the sample size. If we have 2 population proportions, what we're going to have to do is enter these both as lists. So for the first population, 167 of 335 voted. For the second population, 94 of 208 voted. And we want our correction to be false. The question asked us at the 5% significance level, can we conclude that there is a decrease? In other words, can we conclude that P1 is greater than P2? So that means that our alternative is greater. And when we do this, we end up with a p-value of 0.1454. 0.1454. Ignore this chi-squared, by the way. We'll come back and we'll talk about chi-squared tests in the next chapter. That's a chapter 13 issue. But our data here gives us a p-value of 0.1454. That's greater than 0.05, so we do not reject the null hypothesis. We cannot conclude that there were more, that there was a higher level of voting in 2008 than in 2012, just based on the sample. Okay, so we do not conclude that. The part B wants us to find a confidence interval for P1 minus P2. This confidence interval is wrong. Okay, remember that we specifically were looking at an alternative hypothesis of greater. Whenever we talk about confidence intervals, that should be a two-sided. That should be a two-sided hypothesis test. So what that means is I'm going to get rid of this alternative equals greater code. I'm going to put in just this. This is by default going to give us a 95% confidence interval where it's two-sided. And so if we do that, we end up with the right confidence interval that we found in our example. So negative 0.0397 up to 0.1328. Okay, and so there is our 95% confidence interval. Okay, so that's how we use R. That's how we